So today we have Michael from TQ Tezos. So TQ is our joint organizer for this hackathon. So he's going to be talking to us about the FA2 token standard. Going to go through a quick presentation about the design considerations and different details about the token standard, and then do some live demos with the standard. And then, if you have questions along the way, feel free to toss them in the Q&A, and we can do a quick question and answer at the end of this. So, and as usual, this will be recorded on YouTube as well. So if you want to watch it again, it will be uploaded by the end of the day today. So take it away, Michael. Thanks.
All right, hi, as he mentioned, I'm Michael Klein. I'm a senior software developer at TQ Tezos, and today I'll be talking about TZIP12, the FA2 token standard. So just to give a little bit of background, modern capital markets are sophisticated. So we have some sort of capital supply from institutions such as sovereign wealth funds, endowments, et cetera, or even individuals. Somehow this needs to get into, assets, custodians, banks, et cetera. And then of course there's capital demand, which is pushing it through this whole cycle. So where do we fit? Well, all of this part needs a lot of interop. The regulators, lawyers, custodians, banks, et cetera. That's where standardization and using digital assets and on-chain logic can really simplify a lot of things that are done manually or without standardization now, and can really help a lot of these different entities interop with their investment data. So this is kind of like the tech stack of the financial side. So we have on the top, we have like issuance platforms who do, some compliance related stuff when they issue digital assets, qualified custodians that have to be regulated a bit more like a bank or a trust. And then, exchanges that are actually like the secondary market for these digital assets. So then all of these live on top of some sort of asset standard. So if you're familiar with ERC20, all of these issuers and custodians and exchanges likely will interface with ERC20 on Ethereum because it's a token standard for fungible assets. And then finally, at the bottom, we have the blockchain. This is Tezos itself. It's the immutable distributed ledger that allows us to run smart contracts on chain and verify their output in a decentralized manner. And this is where we stand. So why does this matter? Well, when we're talking about digital assets, we need to remember that we have a lot more experience with traditional assets than digital assets. So what do we know about the lifetime of a traditional asset? Well, some of them can be very long, with BNY Mellon being continuously traded on the New York Stock Exchange for 235 years. So we really want to try to find things that won't have to be re-engineered when there are substantial changes in a couple months, couple years, whenever that may be. So what is FA2? FA2 is a financial application standard for a multi-asset interface. On Ethereum, we have ERC20 to represent fungible tokens and ERC721 to represent non-fungible tokens on Ethereum. While FA 1.2, which is like an ERC20 on Tezos, is specialized for a single fungible token contract, FA2 is agnostic to the token type and allows both single and multi-token contracts. This is because it's a standard that specifies an interface, and that interface is designed to work well with both of the assets and not just say, oh, well, we literally just have a standard where we put both, fungible and non-fungible things just right on top of each other. And then so, you'll lose either way if you don't use both. This really aims to be friendly to wallets and external applications that need to deal with both types of assets without caring as much about the details when they're less relevant to standard types of exchanges, swaps, trading, whitelisting, whatever that may be. And to that point, we've pursued making all of the entry points in FA2 into batch operations to allow multiple transfers to be executed in a single atomic transaction. And we actually get that atomicity simply from the properties of Michelson, where if there's like some part that fails, it guarantees that it will roll back the entire transaction, the whole batch. And so this kind of free atomicity we started realizing it's clear that we can use it for things like an atomic swap between tokens, but what else can we use it for? Can we, have people do feeless transactions because it's very cheap to submit a lot of batch transfers all at once, things like that. And so what are some things that this is especially useful for that we couldn't necessarily do with FA 1.2? Well, NFTs for collectible assets where you have many, many, many asset types, they're simply not feasible if you take a standard FA 1.2 that's intended for a fungible asset and you just, make hundreds of them. And then non-transferable badges to incentivize behaviors are also, not really fungible. So we need some extra complex logic to manage that. And then multi-asset contracts containing things like interactive gaming items, derived assets, complex combinatorial combinations of assets, basically. So what are the design considerations? Well, we've tried to get as much feedback as possible, and it's been at, around 24 external individuals and teams from all over the ecosystem that we've been trying to get feedback from, especially people that are involved with these use cases we're talking about. So decentralized exchanges, multi-asset tokens, different sorts of NFT use cases such as games. And so really this comes down to the three main types of considerations. One, what do we learn from Ethereum? Because Ethereum is one of the leading smart contract platforms right now. How do we avoid fragmentation? Because that's something we've really seen on Ethereum, where ERC20 doesn't necessarily interop with practically any of the other very specialized token standards without, heavy amounts of proxying and custom logic. And then finally, how do we be ready for the next protocol? Because as you saw with the BNY Mellon, I mean, if we're looking to make things stable for, literally hundreds of years, Tezos is a upgradable platform that is meant to adapt to the cutting edge of what we can do and, release new upgrades of how everything works. So we need to be able to move with that sort of rapid development. So what am I talking about with Ethereum? Well, in Ethereum, a lot of the adoption for different token type standards is just driven by what gets adopted. The intention for individual standards is kind of like a local, we have a need, we need a solution. So like the ERC20, it is a very generic fungible interface, but it doesn't translate easily to non-fungible tokens. And then you get a mostly incompatible interface for non-fungible tokens. Differences between these standards limit network effects and cause friction for wallets and external applications, practically anyone who needs to interact with this token. So if you think of the lifetime of a user, having a token, they somehow have to enter the platform, acquire the token, know how many tokens they have, be able to trade them with other people, probably be able to trade them for different types of assets, right? Each of these steps requires, a conversation between the previous and the next step. So, whoever gets the person the token needs to be able to be compatible with the exchange, who needs to be compatible with a wallet, who's talking to the exchange to do the trade, et cetera, et cetera. So really our priority is to limit the fragmentation as much as possible and make it a smooth transition between all these different parties that have to talk to have the full user experience. And then permission standardization needs to allow a lot of custom behavior without fragmenting the contract. So there's no free lunch, there's no silver bullet. We can't just say, oh, well, we took these much more complex cases and we made it just as easy as the simplest case. That's not how complexity works. So how do we manage adding complexity incrementally in a way that we can like add or remove it modularly and customize the contract without getting stuck under, bloat or bit rot. So overspecification will restrict what developers can do when they integrate with the contracts, which prevents this nice smooth user path. But under specification leads to a lot of fragmentation, and a particular implementation will just say, hey, I see fragmentation, let's do a value capture on one of those particular things that it's not covered by the main use case. And then instead of helping fragmentation, often those entities won't necessarily be incentivized to merge all of their standards into a single standard, like USB and FireWire. So then the fragmentation just continues effectively. So really you want to try to prevent this from happening as much as possible at the outset. And then future considerations, I mean, I mentioned Tezos is an upgradable platform, and we've had a couple upgrades already, trivial and less trivial, and we're expecting a lot more in the future. So how will this standard react to those sorts of changes? So several of the features that we're thinking about and looking at intently include things like contract signatures, also known as stamps or tickets. These are, you can think of the equivalent of a cryptographic signature or like a public key signature for a contract. So since it's on chain, all the execution is public, contracts can't have private keys. Maybe we could do something with zero knowledge proofs, but realistically they can't. But we can use the existing security of the blockchain to emulate that security effectively, use the existing consensus. So that would allow a lot of interesting interactions, different ways of doing permissioning and authentication, and it's very exciting. Tezos currently does not have any sort of event logging like Ethereum does, and a emit of events would really affect what you could do with these contracts. So currently, like, let's say you want some sort of trigger to happen when tokens get traded in your token contract. In Ethereum, you might model this as, okay, well, when anything happens, we have standardized events. The events pop out of the contract when things happen. We have event listeners on other contracts. They get triggered. They start, doing the things that they need to do given events, and you just get this kind of like reactive, evolving system. Well, on Tezos, you can only really emulate events through callbacks. They're very expensive because they're basically made for arbitrary function calls and not made for these read-only events. And so having a native efficient way to do events would really make some of these multi-contract architectures more efficient and more viable. Read-only calls is something that also is very similar, where when you have lots of contracts all talking to each other, you pay more for a read and write call. And currently there's only read and write calls in Michelson on Tezos. So adding read-only calls would make it a lot easier to store different parts of the contract's data in different contracts without paying lots of extra gas for splitting it up. And then finally, lazy contract loading. So later I'm going to be talking a little bit about a monolith architecture, where you just dump all of your contract architecture all in one contract. And something that developers in production have been running into on Tezos is that you paid the cost in the current version of Tezos to parse and type check the contract, even if you only use a small fraction of the contract itself. So let's say you've got 15 entry points, you have to parse and type check and deserialize from bytes the entire contract, all of the entry points, even if all you're doing is some simple entry point that maybe checks the admin and sets pause or sets unpaused. So this will make it much easier to put more logic into these contracts without having this kind of balancing act between, is it too big that the cheap stuff will be too expensive, or is it too small that we have to, talk between the contracts constantly? So what are our core priorities? Well, versatility, separate the token type from the underlying logic to allow different types of tokenization use cases and easily plug and play sorts of features. Allow one integration with FA2 to open the door to any other token type. That this should really be a smooth transition when you don't have those special cases that aren't just data types. And then it should provide a foundation for complex token interactions, such as using some sorts of hooks or callbacks. Our main use cases involve things like multi-token projects, such as reward points or badges for subreddits or other social media. On-chain game items with complex logic and swaps are a fit use case for this. And then, of course, the main case, which is multi-token DeFi, managing many different types of tokens and assets at the same time in the same platform. So what does it actually look like? What's the architecture of this contract? Well, the entry points really are broken down into three main areas. The token ledger, which is the ERC20 sort of, you have a token or tokens, you can trade them. You have a specific amount, which is your balance. There's a total amount everywhere, so people can't share tokens usually. And then we have permissions, so we need some way of managing actually who can do the token transfers and stuff like that. So we have permissions descriptor, which is effectively metadata for which permissions are enabled in the contract. And we actually have a custom field that will allow you to extend that descriptor with your custom logic. So let's say you have some secondary registry of token metadata, and that registry holds info for all your NFTs, like maybe each NFT needs to be linked to some sort of audit or something. You could say in the permissions descriptor where the contract that would deal with those permissions would lie. And then you can update operators. So quick note, ERC20 is uses allowances, where you say, I have X amount of tokens, but let's just forget that for now. Let's pretend that some of them are yours. So you basically pick a specific number of tokens to allow another user to send on your behalf. And this sounds great. You say, well, I've got 100 tokens. I want to buy lunch. I'm going to take 5 tokens and give the allowance to, some sort of on-chain sandwich company, right? And it seems like it's all great, but the issue is the user doesn't know that it's 5 tokens before they talk to the sandwich company, and the sandwich company wants to just keep the user on their platform. So they effectively ask for all 100 tokens, if not millions and millions of tokens that are far more than the user will ever have, effectively just becoming an admin for their account. So we did some research and we saw that allowance is used in that method where you just set it to a huge value practically every time it is used. And so we opted for a variant, which I believe is on ERC 1155, which is an operator's semantics. So with operators, you can think of it as an infinite allowance. So you give somebody permissions to transfer tokens on your behalf. And there are no restrictions on what they may transfer other than the restrictions already existent on your account. So they don't get, they can't create tokens just because you give somebody access. And then of course you need to check that somebody's an operator for, maybe you have an exchange contract. The exchange contract needs to become an operator to do the swap. It might need to check that it's an operator, or somebody else might need that information. And then finally, extension points. I said FA2 has a high priority to be very extensible, and it really takes a couple approaches to this. One is with token metadata. So there are a couple required fields that we found not having those fields can really make it difficult to integrate, for example, with wallets. And then we have a map that allows you to extend that metadata with other information that you might want to associate with your tokens. The error handling is specified in if you do this, it must behave in a recognizable way. And then otherwise, here's how to put the extra information in it. So it's an extensible error specification that will allow people like wallets or somebody else who's making token related tools to automatically recognize the errors. And these are things like, you don't have a balance, or you're not the owner of the tokens. The most common standard errors are what we've basically put in here. And then finally, one of the most general types of extension points of FA2 is a transfer hook. So like operators give you complete permission to send your tokens, you can think of a transfer hook as having complete permissions to veto your tokens. So whenever a transfer occurs, it's kind of like an Ethereum event, which gets sent to this transfer hook contract, and it can decide to do nothing, in which case the operation will complete and the tokens will be transferred, or it can throw a failure, which will unwind the entire transaction and allow you to prevent your tokens from being transferred. Of course, there are some certain special cases when you have administrators that are like minting or burning tokens from people's accounts that shouldn't be able to be blocked by users. But in general, you can emulate at least some of events and adding custom logic to your account. So what does this look like? I've got a bit of a graph. If you do a monolith, which is what I mentioned earlier, you just put everything in one contract, all of the entry points, all of the permissions. You just have this main FA2 core with your custom permissions and a custom API, and then of course, some sort of transfer logic. With a wrapper architecture, you'd use multiple contracts. So you put your transfer in the wrapper and your custom API, and then link that to a core token contract that implements, for example, a token ledger, the operator logic, permissioning logic, what have you. And then finally, you can also implement many of these types of custom logic using just transfer hooks. So if your logic only needs to say yes or no, allow this transfer, which is a lot of types of restrictions, then you can add it in a transfer hook. So when the tokens are transferred, it'll call the hook, it'll run the custom permissions, and if there's any sort of error, it'll throw a failure, and that will prevent the transfer from occurring. The reason why we use this sort of kind of after the fact architecture is, I mentioned before with the read-only calls and that calling back and forth between lots of contracts is expensive. Something that'll likely be fixed in the next protocol, but isn't currently the case, is if you call from token 1 to token 2 back into token 1, you will pay 3 times deserialization, parsing, and type checking. So to avoid this, if you just go A to B and then fail or succeed, as with the hook, there are fewer calls, there's less deserialization, less parsing, and less type checking. And so this can be a lot more efficient if that's the type of logic that you need that doesn't need to call back and get extra information. So for example, let's say you had a hook that not only needed information about the current transfer, but about maybe somebody else's balance that you couldn't keep track of through just knowing what you transferred. You would have to do an extra callback, and then maybe it would make more sense to put that logic in a wrapper since you're already calling back and forth. So a little bit more detail. With the on-chain wrapper contract, you store the additional logic in a separate contract, like I said, calling back and forth. Some of the pros include you can just change the address that you're pointing to with the wrapper, and that's your upgrade. So let's say one of the components is a whitelist contract, and the token contract just says, who is my whitelist? If you want to change that whitelist contract and upgrade the semantics and do all sorts of things, you can literally just put an operation pointing the token to the new whitelist. And then, people can easily check, oh, who is your whitelist? Where do I find the implementation? And you can expose that in your contract. It makes it a lot easier to share logic and data across contracts if they're all reused in the same place. So like I mentioned, a metadata registry. If you use your metadata registry for maybe, let's say 3 to 5 token contracts, they could all use that same registry contract. And upgrading to the new registry contract is just changing that address. So it's very, very easy to do that. But it's harder when you get to the concurrency, when your application has, in effect, 3 servers or 3 microservices. It's significantly more difficult to reason about what happens. And Michelson is designed so that certain types of concurrency errors and things that can come from impurity plus concurrency are much more difficult, if not impossible, but it is a lot more complex to figure out what's going on and what can and cannot happen. And you do spend a lot of gas calling between the contracts. With the monolith, everything's in the one contract, which is cheaper than calling across the contracts and easier to keep track of, but it's a lot easier to run out of gas from the code size. And it's harder to upgrade because you might have to upgrade everything all at once. It's a lot more likely that, like I mentioned, a really simple entry point like a pause could use much, much more gas because of how big the rest of the contract is. And then finally, with a transfer hook, it's great because it's a standardized way to make plug and play wrapper type contracts that are easily customized to different tokens and users. Because this is a transfer hook standard, you can take your transfer hook and easily use it across different FA2 contracts, which is not the case at all with wrappers. Normal wrapper contracts are completely custom. Who knows how they connect to your token contract? And it's likely involves a lot of admin only logic where like only the admin can even interact with it. So with the transfer hook, it's kind of like a wrapper, but the USB part is standard. You can just plug it into the next FA2 or even use it for multiple FA2s. But it can be difficult to manage different hooks for different users or different cases. And there's no way to know that you don't need to call a hook, which adds overhead to calls where maybe you want to do like some sort of like, I'm just sending tokens to the outbound address where I'm going to cash out of the tokens. And I don't need to call a transfer hook for that, something like that. All right, so at this point, I will be jumping into a brief demo of some things that you can do with FA2. I will be using a copy of FA2 written in SmartPy for a single token. It will specify like the token ID, but the token ID will always be 0. I'll go quickly through the standard interactions you can have with the contract, especially if you're just going from a command line. And then I'll use an operator contract, which is where we make a contract and we make it an operator for one of the users. And then we can basically delegate small amounts of logic to that operator to do things like a batch transaction or a swap between 2 tokens. So jumping into that. So to originate the contract, I'm assuming you already have the appropriate Docker and SmartPy and Tezos client. If you're familiar with Tezos client, to originate the contract, you have this originate contract and the name, transferring the initial balance of the contract from your user address, and then this is the code. So this is how you just get code contract with the Docker tool, called FA2 for FA2, pronounced literally. The initial storage, we just say we want Bob to be the admin. We make the initialization expression with Bob. And as you can see, this costs about 10.3 Tez. So it generates the contract. I'll go real quick and show you what it looks like. So you can see it has a bunch of entry points, balance of, operator, permissions descriptor, etc. And the actual implementation is a bit long, so I won't be diving into the pure Michelson for this, but I will for some of the other contracts. The entry points you can just see here. We see transfer, update operators, mint, balance of, is operator, etc. The main one that I haven't really gone over is just mint. In the code, you can see all of its parameters. So mint, we need an address to mint to, how much to mint to the user, the token symbol, and the token ID. So once we have our FA2 contract, we'll just use the same Docker tool to make that expression. So you can do FA2 make mint expression to Fred 10 tokens. And as you can see, this is a lot less than 10 Tez, about 17 Tez cents. And then we can transfer a token from Fred to Alice. So we're still sending this from Bob because Bob is the admin and can do whatever he wants, but we're just sending one token from Fred to Bob on the token ID 0. Because since it's a single token, there's only one token ID, and we specify that it must be 0 so that it's easy to not be confused between different tokens. And then to view a balance, if you notice on this contract, for balance of, it requires a callback along with a list of requests, and the callback's actually a contract. So since we can't simply return values on Tezos, we need to provide another place for it to put them. And this is what I'm calling a view contract. So this view contract all it does is fails with, well, here's the code right here. So it accepts the list of the balance, the request, the token ID that we see as in the callback for get balance, and then it just fails with it. So we'll be able to read what the balance is. So you just make a bash variable for that, and we can actually just call it using this. So we transfer from Bob address to FA2, but this can be from anyone because all of the get balance and other informational entry points are public. We specify the entry point in the Tezos client, and we give it the pair of the contract where we're going to return the balance, the view contract, and the address that we want to look at, and the token ID, which for a single token is always 0. This takes about 7 Tez cents, but it doesn't actually run because it fails. And we can see it fails with this. So this is the user. 0 is that token ID. And this first value, which we'll be seeing in a couple more examples, is 19 because they had 20 tokens and transferred 1. We can also view the balance of Bob, and Bob has 1 token because we transferred 1 token from Fred. So then what does a batch transfer look like? Well, if you noted in the type of the contract for the transfer, so transfer has a list of transfers really, because it's a batch transfer. So we can just, in the FA2 application with make transfer expression, we can just give it a list of transfers. So transfer 1 token on token 0 from Fred to Alice, and then transfer 1 token on token ID 0 from Fred to Bob. So this emulates something like maybe like a dividend distribution, or potentially could be a batch setup of many accounts. If you're doing your KYC and you find that the individual transaction to add a user is pricey, you could potentially try to max out your batch, which is probably around 200, and add lots and lots of users at once. And then of course, if it's not like a dividend, you are adding users, they probably have different initial balances, but maybe they all have the same for some reason. And then just real quick what this looks like with the batch. So we call this transfer entry point, just calling from this Bob address to the token contract, costs about 2 Tez cents. Well, sorry, in total it costs about 7 Tez cents, or about 250,000 gas. Here we see this is the parameter, the batch gets all pulled out. We have the from and to addresses, token ID 0, amount 1, and then we can see the updates of the storage. So updating all of the balances. And then you can see that we touch, well, this just tells us that we have operators from other parts of the examples. Let's see. And just real quick, what the FA2 in Smart Pi looks like. It just mostly looks like Python. So there's some decorators to tell it that certain functions or methods are entry points. But then you can basically write it as if you were writing Python most of the time. You need to do this SP thing, which tells you that it's Smart Pi, it's Tezos related and not, you shouldn't treat it as raw Python. But besides that, it's pretty straightforward. And that is the initial example of what you can do with FA2. It really looks a lot like batches plus token IDs plus ERC20. So I wanted to really show off a bit more of the use cases with operators and batches. So I have an example where, so we have this operator contract. Let me go down to it. So this is a contract that you make an operator for your tokens, and you store a batch in the contract, and then anyone can ping it. You don't have to be the one who pays the gas. When anyone pings it, it will execute the batch. So to just quickly go through, so this is the unit default parameter, which is basically just saying all you can do with this contract is ping it or send it tokens. You can't give it any information. The storage is just the the address of the FA2 you want to send it to, and then this is exactly the type for a batch transfer. So all we do is, in the code, is get the storage, hold on to the previous storage, and then unpack it, make sure that the address, the FA2 address, points to an actual FA2 contract, or the transfer entry point of an FA2 contract. Make sure it resolved, set up the transfer, and send that batch to the contract. And then the rest of this is just cleanup. So effectively, this is just a contract which acts as a user and will execute the batch. So what do we need to do to set it up? Well, first we'll have to originate it. So just like before, we have this originate contract transferring from Bob address, running the contract code. And then we initialize it with the FA2 address at the transfer entry point. That's that little % symbol. And then this here is the make the transfer expression. We want to do that batch transfer just like before. Send one token from Fred to Alice and Bob on token 0. And as you can see, this costs about 60 test cents. So this goes through just to create this batched contract. We make an address for it. We need to make it an operator. So this is new. It looks just like the other transfers where we use the Docker, except we call make update operators expression. And we do this add batch address, Fred address 0, which adds batch address as an operator to Fred for the token 0. And as you can see, we have to call the entry point update operators here. And that takes about 2 test cents. It's very, very efficient. And then finally, if we ping the batch operator, it'll actually perform the batch. So we just say transfer 0 tokens from Fred address to the batch address, though really it could be from any address to the batch address because this is not authenticated. And it will attempt to do the entire batch of transfers from Fred to the user, well, Alice and Bob, right? So we call transfer on this contract, and we should see some internal operations. Let's see. Yeah, there's one internal operation. Yeah, so internal call transfer. So this is just the call to the original operator contract. And then this internal call transfer, it looks very similar because this is just the batch transfer that we did manually from a single user before. The benefit is, so let's say you have some sort of fixed dividends that are not updated quarter to quarter, but they need to be released to your users quarterly. And so you have an account that holds the funds that are released to the users, and you know your list of users that you need to give dividends to. So you could use this contract where the batch is the fixed dividends with all of the users that you need to send it to. The account, the owner of the tokens that is going to, this is going to be the operator for, will be your distribution account. And then when the time comes, you add the tokens to the distribution account, and anyone can ping it and actually run the batch. And so you could have basically like a feeless distribution where even though you're still paying to transfer the tokens into that main distribution account, somebody else can pay to actually distribute them. All right. And then my final example is a swap operator contract. So instead of just sending a batch, what if we want to take advantage of that atomicity that I talked about earlier, where if we do a batch and we can send between 2 people, we can actually do a trade. Well, this is a little bit more complex because on a single token asset, if we just do a swap of like, you know, one token of one token, and they're the same type of token between 2 users, you know, the start situation and the end situation is the same. They both hold 1 token. You can't really tell whether it succeeded. So I created 2 FA2s and an operator contract like the batch operator that instead of sending a batch all from one person, or really, you know, whatever batch you want, but all to one contract, all one token type, instead the swap operator contract accepts two FA2s, and it will swap one token between two users on those FA2s in an atomic manner. So let's take a look at that. So first of all, the contract itself to do the swap is a little bit more complex because it has to deal with calling two contracts instead of just one contract. But the parameter is pretty similar to what we had for the storage previously. You give it two contracts that accept this. This is the type of the transfer entry point. And it will swap between the user that made this contract and yourself. And so it needs to store who made the contract. And then I'll just kind of skim through the code. This is a little bit harder to read because it has an optimization. If you simply built up the transfer tokens call for each contract from scratch and inlined everything, it would take twice as much work to do the parsing and type checking of the code. So instead, I make a list of transfers to arbitrary contracts, and I say bool true or false to say whether the seller is to or from, and then we just iterate through that list with only two elements. But effectively, if you can see, like here, this is the same exact code as before. We just need to make a batch and send it to each of the contracts. We actually just push the pair directly like this, and we say, well, the token ID is 0, and we want to send one token to and from these two users. So what does this actually look like? Well, when we actually, first of all, we're going to need a new FA2, and this is just as the same as before, actually the same command. We just want to name it something different, so we'll have a different variable for it. Just like before, we meant 10 tokens to Bob. Well, I guess before we meant them to Fred. Then we need to create this swap operator contract, which costs about 66 Tez cents. And of course, make a variable for it. And then as before, we need to make it an operator for the people that it's going to send tokens from. So we'll need to make it an operator for both Bob and Fred. So here we call the original FA2 just as FA2 address from Fred, because he's the only one that can make people operators. And we just say, okay, take the swap address and make it an operator for Fred address on token 0. That costs about 2 to 3 Tez cents. We do the same exact thing on the new FA2 address for Bob. See, we make the swap address the operator for Bob with token 0. And then finally, we check some balances just to see what the state is before we do anything, using the same callback method. So we can see that Fred address on the original FA2 has 16 tokens on token 0. And then Bob address on the new FA2 has 10 tokens on token 0. All right, so then to actually do the purchase of one of the tokens that Bob is offering, because effectively Bob is offering a one-to-one trade, as many as you like, between the two FA2s. It's basically any FA2 where I have tokens and you just provide another FA2, I'll just do the swap. So in theory, we should probably be checking that, the FA2s that he's buying represent something that he wants to buy, but this is just a simple example. So we just say transfer 0 Tez from Bob to the swap address, because Bob's the one who wants to do the purchase from Fred. And he'll send the entry point plus the address for the FA2 address he wants tokens from, and then his FA2 address. And this will cost about 7 Tez cents. And this will do the full swap. So I'll check the balances real quick, but then we can look at the internal transactions. We see that Fred now has 15 tokens and Bob now has 9 tokens. And then they'll have 1 tokens on the other exchange. Sorry, not the other exchanges, the other token contracts. If we look at this transfer, it has 2 internal transfers instead of just the 1. So we can see a little bit more what the multi-contract architecture will look like. So this is just the call default entry point on, so this source is my Bob address. This destination is the swap contract, as you can see. And then this destination, the final destination of the 2 internal transfers, this is the FA2, the 2 FA2 contracts. So each time we will send from and to, except swapping the from and tos for the 2 cases, token ID 0 and amount 0. And since you see the consumed gas is around 32%, and really we won't expect to be able to do maybe between swap between 5 contracts or 4 contracts. That probably will be over the gas limit with the max gas of, I believe it's around 1.2 million, something like that, since Carthage. And that is about it. Here we have, see that they all update, and that concludes my talk. Thank you so much. And do you have any questions?
Awesome. Thanks a lot, Michael. Yeah, does anyone have any questions? Feel free to toss them into the Q&A. Seems like no questions so far. Cool. Yeah, thank you guys for joining again today. We are, as I mentioned, going to upload this to YouTube. The hackathon is starting next week, so you will get an email about the beginning of the hackathon as well. But yeah, thank you all for coming. Thank you again for your time, Michael.
Thank you. Have a great day.
Have a good one, everyone. Bye.
Take care.